Thank you very much for the introduction. It's very cool to be here virtually today. So today I would like to talk to you a little bit about different geometric sites of Lagrangian dynamics. So first of all, a little bit about the role of dynamics in robotics. So as you can see, humans are naturally able to generate skillful dynamic motion. This is a little bit of an extreme, but generally we are actually able to have kind of an intuition of what we can dynamically do. And we can then use it to basically move our body. And the intuition here is that by understanding those dynamic principles, we could actually take inspiration from them and use them to produce efficient or skillful robot motion. So this is a little bit again of an extreme, but you can think about dynamics as something that can also help you produce dexterous, reliable, and energy efficient motions of other types of robot in various types of tasks. So dynamics can help us for motion generation. And then dynamics are not only important to move the robot body, but they're also important to move, to define how the robot should interact with objects in the environment. So again, taking inspiration from human, we kind of managed to build an intuitive understanding on how, what the dynamics of different objects are and how we can actually then act on those objects as a function of those dynamics. And this is valid here for different types of objects. So it can be solid object, but also deformable objects, either volumetric deformable objects, or also something that is a little bit more flat like clothes. So basically dynamics are also useful for manipulation and interaction. So I think we can agree that dynamics are ubiquitous in robotics. And an important point that in many cases, the dynamics are actually high dimensional. So all the examples that you see in these slides are actually high dimensional dynamics, and they're also highly nonlinear, so they're complex. So how do we usually represent dynamics? Very often we use Lagrangian mechanics because it provides a powerful framework for modeling the dynamics of physical systems based on principles of energy conservation. And those Lagrangian dynamics can describe the motions of many mechanical systems, including the ones I'm going to talk about today, so humans, robots, and rigid and some of the deformable objects. So just to give you a little bit of a recap, I guess everybody's a little bit familiar with Lagrangian dynamics, but just so that everybody's on the same page. So in Lagrangian dynamics, we define the Lagrangian, which is basically the difference between the kinetic energy and the potential energy of a system. And very often the kinetic energy has this quadratic shape where the mass inertia matrix of the system multiplies its velocity. Based on this Lagrangian, we can derive the Euler-Lagrange equation, which also contains the external generalized force. And then this basically gives us a second-order differential equation, which we can solve, and it gives us basically the motion of the system. So we can take a little bit more of an intuitive look on this, and we can interpret Lagrangian dynamics from a geometric point of view. So in that case, the configuration space, so essentially the space of joint configuration, can be interpreted as a nonlinear manifold. So you can see that as a high-dimensional surface, which is curved. And the curvature or the properties in general of this high-dimensional surface are entirely characterized by the mass inertia matrix of the system. And then basically by characterizing the dynamics in that way, the enforced equation of motion are simply the shortest path on this mathematical space, on this curved space. So what I would like to do today is to show you how we can use this geometric perspective on Lagrangian dynamics for understanding human motion and generating robot motion. So here we're going to use this first geometric site, which is the configuration manifold, and we will analyze human motion through the lens of geometry and see how we can then transfer them to robots. And then we will even see how we can actually influence on the geometry of that space to avoid certain region and obtain, for instance, collision-free robot motion. And then in the second part of the talk, I would like to take a perspective where we actually don't know the dynamics, we are learning them. And here what we will do is that we will account again for the geometry of the configuration manifold to learn those dynamics. And then we will have two different geometric perspectives. So the first one about the geometry of the mass inertia matrix that will allow us to learn this mass inertia matrix. And then a geometric perspective on reduction mappings, which will allow us to reduce the dimension of possibly high-dimensional Lagrangian dynamics and learn the dynamic parameter in a lower dimensional space. So let me start by a little bit of theory. on the geometric space that I'm actually considering. So the three geometric space I already mentioned are all Riemannian manifolds. So intuitively, those Riemannian manifolds are mathematical space that locally look Euclidean, but are generally curved. What that means is that for every subset of the manifold, you can find a homeomorphic, so a one-to-one mapping, essentially, to a subset of the Euclidean space. This allows you at each point of your manifold to define a tangent space, which is a space that is linear and tangent to the manifold at a point. And on this tangent space, you can define what is called a Riemannian metric. So this Riemannian metric is crucial because it gives you basically the entire intrinsic geometry of the manifold. So if you know this metric, you know everything you need to know about your space, essentially. And this metric smoothly varies on the manifold. So it allows you to define the notion of norms between vectors, the notion of length of curves and of distances between points on the manifold, and also the notion of shortest path, which are also minimum energy and minimum length curve on your space. Then we have here some important tools that we will use through the talk. So the first one is actually the exponential map, which allows you to map a vector from the tangent space onto the manifold. And then the inverse of this is the logarithmic map. And a last operation that is important is the spiral transport, where you move a tangent vector from one tangent space to another in a geometrically consistent way. So this is a very big topic. I really give you like a crash course in 1 minute on Riemannian manifolds, but I think this should give you roughly what you need to know to then follow what's coming. So why I'm talking about Riemannian manifold? First of all, because the configuration space that I mentioned before is an instance of a Riemannian manifold. So in that case, each point of the manifold is a joint angle, and the Riemannian metric, so the one that defines entirely the geometry of your manifold, is the mass inertia matrix that we saw before in the Lagrangian dynamics. So then basically we can see this configuration space as a Riemannian manifold, whose geometry is characterized by the mass inertia matrix. Now what is interesting is to actually have a look at what are the shortest paths on this manifold. So what are the geodesics? And basically they follow this equation, which again, you recognize this is the classical dynamic equation of motion, which is without potential and without external force. So this means that shortest path on the manifold, so geodesics, correspond to passive minimum energy trajectories of the robot at hand. So now we would like to use that fact to analyze human motions. So when you think about the configuration space of a human, you can also see the human as a kind of mechanical system. So we can then analyze human motion through the lens of geometry and of Lagrangian dynamics. So one popular hypothesis in the human motion literature is that human movement follow minimum effort path. And from a geometric perspective, actually, that simply means that human movements follow geodesics, so shortest path in the configuration space manifold. So this hypothesis has been analyzed in the literature, here typically for a 4 degrees of freedom arm, and then later here by Nelson et al. That presented the geodesic synergy hypothesis. So the idea here is that human motion follow basically, when you have a point-to-point motion, this point-to-point motion will follow a geodesic, so a shortest path in the configuration space manifold. So what we did is that we brought this hypothesis one step further, and we hypothesized that complex human movements can be modeled as sequences of those geodesics, so of those geodesics synergies. So to validate this hypothesis, we needed 2 steps. So first of all, we needed, given a ground truth human motion, so a motion that we measured, we wanted to segment this motion into several geodesics, so several chunks of shortest path, if you can say it like that. And to do so, we developed this segmentation algorithm, where basically what we do is that we know that along a geodesic, the velocity is constant. So what we can do is have a look at what would be the velocity at the next point if you would be on a geodesic. And then we check the difference between the current velocity that we observe and the velocity that we would have if we would be on a geodesic. And basically, as long as those 2 vectors are closely aligned, it means that we are still on a geodesic. And when this changes and we have a big angle basically between the current velocity vector and the one that we're expecting, it means that here we have a breaking point, and basically we are starting a new geodesic, a new synergy. Once we have all these segments, what we want to do still is to verify that each of the segments indeed corresponds to a geodesic. So we basically reconstructed the motion by starting at the initial point and building the geodesic from the initial point to the final point of each segment. So we analyzed several complex human motion using this segmentation and reconstruction algorithm. So here I will show you an example. We have here this ground truth motion. So it's a pointing motion at 3 different heights. And I will show you the reconstruction that we obtain using this Riemannian segmentation and reconstruction approach. And then I will compare that with what we would obtain if we would consider that the configuration space manifold is actually flat, if it's a Euclidean space. So it means that we don't have any notion of nonlinearity in there. So you will see now the motion that we reconstruct. So it's a little bit hard to see, but you can observe the elbow. This is where we see most the difference. And then you can see the difference also here on the trajectory of the hand, basically. So you see that the trajectories of the hands are very different. They're in red in the Riemannian case and in blue in the Euclidean case, and they are clearly very different. Now we can compare, okay, so here for the color, the Riemannian is supposed to be here in red. So you see here the ground truth in black, the Riemannian path in red on the figure, and then the Euclidean path actually in blue. And you see that the Riemannian path matches exactly the ground truth. So here we are plotting the position, 2 of the position of the end effectors of the hand. Now we can have a look at joint angle. So the color code is the same. Here we plot 1 joint angle of the wrist, 1 of the elbow, and 1 of the shoulder. Again, the ground truth is in black, and you can see that the Riemannian reconstruction, which is here in red, perfectly matches the ground truth, while the Euclidean one actually is quite off in several places. So what this tells us is that our Riemannian model basically successfully allows us to predict hands and joint trajectories of the human arm. So having shown that human motion can be represented as sequences of geodesics of shortest path on this configuration space manifold, we would like to be able to exploit the same principle to generate energy optimal dynamic robot motions. So remember here that basically geodesic gives you minimum energy motion. So it means that humans are essentially following energy optimal path, and we would like to exploit that for robots. So essentially what we would like to do is to be able to transfer human motions to robots such that the main characteristic of the motions are conserved, but by adapting the trajectory so that the trajectory itself is optimal for the joint space of the robot. So here we proposed a transfer approach in 3 steps. So first, we get a human motion. We segment this human motion using the segmentation approach that I previously described. Then we map the start and the endpoint of each of the synergies from the task space of the human to the task space of the robot. And finally, we link the start and the endpoint of each of each segment by using a geodesic in the robot configuration space manifold. So here is an example. We have here the same human motion that I showed you before. And then we basically transfer this motion to here our Armor 6 robots at KIT. And here we observe basically that the motion is reproduced by the robot, that the trajectory overall looks like the trajectory that the human demonstrated, but the robot basically generates a motion that is optimal for its own dynamics. It's energy minimizing for its own dynamic. So basically we are able to transfer the main characteristics of the motion, but we have a motion that is optimal for the robot at hand. Okay. Now it could happen when we want to generate such motions with a robot that we actually have regions that we don't want to go in. So you can think about, for instance, joint limits, or if you have obstacle in the task space, you would like the robot to avoid those regions. So what we propose to do here is to basically vary or influence the geometry of the configuration space such that the trajectories that we generate avoid those regions. So what we do here is that we basically modify the Riemannian metric of the space. So here the M is our mass inertia matrix, which define the Riemannian metric, so the full geometry of the space. And we augment this metric with a collision avoidance metric, which will allow us to avoid the no-go region. So this collision avoidance metric is built based on barrier functions. So the idea is that you take the direction from where you are to the no-go region, and this basically defines this term that is B, and the full metric is basically the identity matrix multiplied by this barrier function. So what it does is that the metric close to no-go region becomes very, very high. So it gives paths that are longer and longer the closer you go to the no-go region. So at the end of the day, the length of the path going through the no-go region is infinite, and the robot will never go there because we are following still the shortest path on the configuration space manifold. We can also modify, so basically define a metric that accounts for obstacles that are in task space. So we use for here the pseudo-inverse of Jacobian to do so. And here is basically what it gives. So here we have a robot motion that follows a geodesic in the configuration space manifold. So here you see it's basically something that looks like a straight line. And then what we do is that we add here this table on the way. And then we had collision avoidance metrics. So one for the joint limits, one for self-collision avoidance, and one for the table. So this geo is for the obstacle. And then we follow geodesic in that new configuration space manifold. And you see that this allows us to avoid successfully the region that was with an obstacle in task space. We can also use this approach when we are transferring motion, following what I presented in the previous slide. So here we have a human motion, and here we are reproducing it with the robot, again, as a sequence of synergies of geodesics, which is adapted to the robot at hand. And here you see that this is really just the geodesic in the robot configuration space, and I'm putting an obstacle in the middle, and the robot, of course, doesn't avoid it. And then we add this region avoidance term, and you see that the robot actually nicely avoids the obstacle. And what's interesting here is that it avoids the obstacle in a way that we are as close as possible to the original geodesic. So it means that the motion is as energy efficient as possible, given the fact that we have this modification of the metric. So in other words, we are generating motions that are as optimal as possible. They are optimal for the robot at hand. They are still energy minimizing, but they are collision free, and they all account for the robot dynamics. So the idea for this part was to account, or to basically have geometry that is coming from this Lagrangian dynamics. So to account for the geometry that naturally arise from those Lagrangian dynamics. And this allows us to simply generate dynamic robot motions that actually correspond to energy minimizing trajectories and that are optimal for the robot at hand. Okay, so in this full first part, I was rather talking about how to move the robot body, how to understand how the human body moves. And now I would like to have a look again at the second motivation that I had, which was how we can actually understand the dynamics of the objects to be able to interact with those objects or to manipulate them. So here, what I would like to talk about a little bit is how we can actually learn Lagrangian dynamics. So the setup here changes compared to what I presented before, in the sense that when we consider the motion of the human body or the motion of the robot, we actually assume that we knew the dynamic parameters. We knew what was the mass inertia matrix, we knew what was the potential energy, and then we were working with that. Now, in that case, you can assume that you see an object for the first time, and you don't know how this object reacts. So you don't know when the robot actually interacts with the object, what is going to happen, what will be the trajectory or the motion of the object. So in that case, we're interested in learning the dynamic parameters of the robot. So we follow the same Lagrangian dynamics as before, which lead to the same equation of motion. And what we can do to predict the dynamics is typically learn a network or learn a model. Typically, the brute force way to do that would be to say, okay, you plug in the position of your system, the velocity of your system, and you get out the acceleration, then you learn the dynamics. But we can do that a little bit smarter by accounting for the fact that we know that this object is actually fulfilling or is characterized by Lagrangian dynamics. So what we can do is to have instead a network that is basically composed of two parts. So one part is a network for the potential energy, which is here in purple in the graph. And then we have a second network, which basically predicts the mass inertia matrix at a given position. And then instead of simply predicting the acceleration, what we do is that we take the dynamics from the equation of motion, we plug in the two networks that we learned that gives us the mass inertia matrix and the potential energy, and we obtain the acceleration via the inverse dynamics, essentially. For the mass inertia matrix, what we have to do is that, so the mass inertia matrix is basically a symmetric positive definite matrix. It means that it has to be symmetric and it has to have only positive definite eigenvalues. So the trick that is usually used to ensure that the mass inertia matrix is valid is to use this Cholesky decomposition that you see here at the bottom, where we have basically that the mass inertia matrix is L times L transpose with L, the Cholesky decomposition. And we train this network simply by basically minimizing the error between the acceleration that we predict and the one that we observe. And the full advantage of this formulation is that then we actually have a model that is physically consistent. We know that we have Lagrangian dynamics, and basically this model that we have conserves the energy and conserves the property that are there when we do have those Lagrangian dynamics. So here on the right, you can see some results with this simple network. So this is a network that was presented by Michael Luther and Jan Peters some years ago. So here is simply exactly their architecture, basically. So we have the ground truth pendulum here that was in, sorry, play the video again. Exactly, so we have the ground truth pendulum that is in gray, and then we have the prediction here in yellow. And what you see is that at the beginning, it's actually quite fine. We are able to predict the motions. But then when we start being further away in time, so basically long-term predictions are getting worse and worse. So this network is cool because it allows us to have physical consistency and it's data efficient, but it allows us only to predict things short-term. And also it's very limited when we want to go for higher dimensional systems. So this is where the second side of Lagrangian dynamics come in. It's how can we actually improve the performance of this network. So one way to do this is to account actually for the geometry of one of the parameters that we are learning, which is the mass inertia matrix. So as I told you, this mass inertia matrix is a symmetric matrix. So you see that here in 2 dimensions because the off-diagonal elements are the same. And it's positive definite, which means that all the eigenvalues of this matrix must be positive. So if you account for those constraints, basically you can represent the space of symmetric positive definite matrices as points that are lying inside a cone. So here it's a cone that is embedded in the space of symmetric matrices, and all the matrices which are positive definite are points inside the cone. So this is again a Riemannian manifold, and you can also see that because if you try to typically extrapolate between those matrices in a linear way, you actually go out of the cone. So what we need to do is again to basically put some geometric structure on that space so that we obtain shortest paths that are guaranteed to stay in the manifold. So here, compared to what we had a little bit before, we have that every point on the manifold is a mass inertia matrix. And the metric is given by yet another matrix. So here the metric is given by this G. Here I don't have an explicit form for it, but this is basically this matrix that is defining how the mass inertia matrices are characterized in the space. So if we use basically the fact that we know that those mass inertia matrices belong to this manifold, it's guaranteed that what we learn with the network, if the networks account for this fact, that all those matrices actually are valid. They are symmetric positive definite. So you can tell me, okay, cool, but basically you're just doing the same as what Cholesky does. So what's the problem with Cholesky? So the issue when you simply consider a Cholesky decomposition and you don't put any additional geometric structure on it is that the distances between two Cholesky decompositions actually do not correspond to the distances between the two mass inertia matrices that this Cholesky decomposition represents. So you can see this here on the plot. So here it's an example where we basically have some clustering in the space of symmetric positive definite matrices, and we cluster on the top based on the Riemannian approach, and at the bottom we cluster based on Cholesky matrices. And what you can see is that when you cluster with Cholesky matrices, you have matrices that are clearly close to each other. So you see typically the two here at the bottom. I'm not sure if you see the mouse, I hope so. So the two here, they are oriented the same. They're just kind of, one is smaller than the other. And the Cholesky classification actually classifies them into two different clusters, because the distance between the Cholesky decomposition doesn't reflect the distance that is actually there between the two matrices. So this is why Cholesky is not ideal. So what we can do to improve those Lagrangian neural network is to introduce geometry from the side of the mass inertia matrix. And instead of having a Cholesky network, we have a symmetric positive definite network. So the idea here is that we have a neural network which is composed of three parts. The first part, so the mass inertia matrix is a function of the joint position, right? So the first part of the network is basically a simple MLP, which maps the joint position towards a symmetric matrix. So a symmetric matrix, which is still Euclidean. Then we have a second part where basically the symmetric matrix is mapped using the exponential map from the tangent space of one point in the manifold. So here this point P, and this symmetric matrix lies on the tangent space of the point P. So we map it onto the manifold using the exponential map. And now the idea is that already here, basically, we are guaranteed that this matrix is symmetric positive definite. And then we can add yet another layer, which is an SPD layer, and it's basically the equivalent of an MLP, but on the SPD manifold. So it accounts for the geometry of the space. And with that, we can have a look at what type of results we obtain. So here you have on the left, the prediction of the symmetric positive definite network, and on the right, the prediction of the Cholesky network. So you see that considering the geometry of the mass inertia matrix clearly helps in having longer term predictions. So now we have a network that is physically consistent. Because of that, it's data efficient and the predictions are improved. What we are still missing is that those networks actually really don't scale with the dimensionality. So they are fine with, let's say, 2, 4, eventually 7 dimensions. But higher than that, usually they just break. So what we can do here is to, again, exploit our first geometry of Lagrangian dynamics. So we can exploit the configuration space manifold, the same as what we saw before. And here is where we have geometries that are a little bit intricate, because you can see here that actually in that case, the manifold is the manifold of joint angles, and the mass inertia matrix is actually the Riemannian metric of this manifold. So basically, we have a manifold that is characterized by a quantity that lies on another manifold, which is here this mass inertia matrix, which itself is an SPD matrix. And in that case, trajectories on that manifold are basically trajectories of the object that you want to identify. So here we have an example where we have a cloth that is falling on a sphere, and basically the dynamics of the cloth are characterized by Lagrangian dynamics. So we have the same geodesic equation, we have the same equation of motion, and the geodesics in the configuration manifold still corresponds to the unforced equation of motion. So we can use this geometry of the configuration space manifold to now learn high-dimensional Lagrangian dynamics. So the fact that we exploit here is that we, again, have this configuration space manifold. So we have basically points on the manifold are joint configuration, points on the tangent space are joint velocities, and we have this Lagrangian dynamics. So the intuition here is that now when we have those high-dimensional equation of motion, they can often be approximated by a surrogate model, which is much lower dimensional. And the idea is that this surrogate model, to be sure that the surrogate model is also physically consistent, it will preserve the structure of our full order model. So basically what we are aiming at designing here is a reduced order Lagrangian, which basically is embedded into a high order Lagrangian system. So what that means is that basically the reduced, so the low dimensional system is also characterized by Lagrangian dynamics through this embedding. And it also means that basically we can map the position in the reduced order space to the position of in the high dimensional space and the velocities as well through this embedding. So this embedding here, phi, is actually the key because it really allows us to map points in the low-dimensional reduced order model towards the high-dimensional order models. So the dynamics of the reduced order model are also mapped into the full order model in a sense. And actually those dynamics in the reduced order model, they are characterized based on the dynamics of the full order model and based on this embedding. And what is very important here is, as I told you, that the reduced order model basically preserves the full order model properties. And this, by properties here, I mean energy conservation properties and also stability properties if you have a controller in the full order model that is, for instance, stable. So what then we can do is to, instead of learning the dynamics in the high dimensional space, we actually learn the dynamics into the low dimensional space. So we jointly learn basically the dynamics in the low dimensional space with the same network as I showed you before, so this SPD network. And then we also learn with the dynamics the embedding. So the embedding here is this mapping that goes from the low dimensional system to the high dimensional system. What we're still missing here is actually now, let's say we have the dynamics, we are predicting the state of the system, and now we would like to update our information. So we now observe again the state of the system, and we would like to put that into the network to basically refine the predictions. So we don't have any way for now to actually take the current high dimensional state and input that into the network. So to do so, we need to exploit yet a third geometry of Lagrangian dynamics, which are so-called reduction maps. So in our system, we have this embedding that allows us to go from the reduced order model to the full order model. And what we want to do is to have an inverse of this, which will allow us to map a point in the full order model towards a point in the low dimensional model, in the reduced order model. So this is called a reduction map. And in order to be able to have a reduced order model that preserves the properties of the full order model, what we need to have is that this reduction map satisfies the projection properties that are here. So basically, those means that the reduction map should be a left inverse of the embedding. And if we satisfy those properties, what we can do is to basically have an autoencoder structure where we have an encoder that maps points from the high dimensional configuration space to the low dimensional configuration space. There we can predict dynamics. And then once we have the predicted position and velocity, we can then map that back onto the original high dimensional system via the embedding. So to satisfy those projection properties, we actually need to have a constrained autoencoder. And the idea is that here we basically have each layer, which is the left inverse of the corresponding layer. So each layer of the encoder is the left inverse of the corresponding decoder layer. And for that, we have this type of layers that you see here. So we have a bias term, which is the same for the encoder and the decoder layer. Then we have weights, which are here, those two matrices. And we have activation function here, sigma minus and sigma plus. And what we do is that to ensure that the encoder is the left inverse of the decoder, we have so the activation function are the left inverse of each other, and the weight should actually satisfy the fact that the weight of the encoder transpose times the weight of the decoder should be identity. So this is the very important constraints, which is non-trivial. And the way to actually account for these constraints is to account for the fact that the pair of matrices that we have here belongs yet to another type of Riemannian manifold. So this is called the biorthogonal manifold, and it's the pair of matrices which, when you multiply them, they give you identity. So what we need to do to learn this autoencoder is to basically be able to optimize those weight parameters. And what we do is that when we do this, we could either have a constraint optimization where we are minimizing our loss and we constrain those matrices to be bio-orthogonal. Or what we can do is to account for the fact that they belong to this manifold and actually have an unconstrained Riemannian optimization to optimize those matrices. So the Riemannian optimization works as follows. So here we have just an illustrative examples. Those biorthogonal manifold is not a sphere, but the sphere is kind of the simple way to visualize it. So we assume that we basically start at a given point and we have a search direction for our optimization. And what we want to do first is to find the next iterate. So we first solve a line search problem, which tells us how far we have to go along the search direction in the tangent space. And then we find basically the next iterate by using the exponential map to map the search direction from the tangent space onto the manifold. Then what we want to do is to find the next search direction. So here what we do is that we first parallel transport the previous search direction from the previous iterate onto the next iterate. And then we compute the gradient of our loss function, which also lies on the current tangent space. Then the next search direction is basically a combination between the previous search direction and the gradient. And we iterate this until convergence. And basically what we do is that we include this Riemannian optimization into the optimization of the network, and we use it to optimize the weight parameters of the autoencoder. So this is the final architecture that we get. What we have is basically an autoencoder structure, which is constrained. So it means that the encoder on the left and the decoder of the right so the encoder is the left inverse of the decoder. And then what we have is that in the center, we have this Lagrangian neural network, which learns the reduced order dynamics. And those are learned via symmetric positive definite networks, which account for the geometry of the mass inertia matrix. And we train this system by basically minimizing the reconstruction error for the autoencoder. This is the part of the loss you have on the right. And then we minimize the error of the Lagrangian network in the reduced order space. So this is the one that you have in the middle. And then we also minimize the prediction error in the high dimensional space, which is the third part of the loss. Okay, so here are a few results. So we applied this approach to learn dynamics of deformable objects. So here we have a row, which is 192 degrees of freedom. So it's a space that is of dimension 192. And you see here the ground truth and the prediction that we can obtain with the model. So they match each other pretty well. And then we tried for an even higher dimensional system. So here we have a cloth, which we represent as a 600 degrees of freedom state space, basically. And here we have a short horizon prediction. So it means that every 25 step, we basically input the current state of the object that we measure to the network so that it can refine the prediction. And here you see that the ground truth actually, the prediction, matches quite nicely the ground truth. So what we did is to try to push a little bit the system even more. So now we actually predict 2,500 steps without giving any feedback on what is the current state of the object. And you see that at the end of the run, we observe a little bit of a glitch. But other than that, even for a very long-term horizon, the model is actually able to learn and predict the dynamics of the object. So what this network basically gives us is that we are able to have physically consistent prediction. We are data efficient. And then thanks to the geometry of the Lagrangian and of the different components, we are able to actually predict the dynamics of high dimensional system and to obtain long-term predictions. So in conclusion, what I wanted to show you today is 3 different sides of Lagrangian dynamics. So first of all, how we can consider the geometry of the configuration manifold for motion understanding and generation. So this allowed us to simply generate dynamic motions which correspond to energy minimizing trajectories and that are optimal for the robot at hand. And in the second part, we basically took a point of view where the dynamics of the object of interest are unknown, so we are trying to learn them. And here we accounted for the geometry of the mass inertia matrix and the geometry of reduction mappings, in addition to the geometry of the configuration manifold. And based on that, we were able to obtain physically consistent predictions, long-term predictions, and to be able to learn the dynamics of high-dimensional system in an efficient way. So I hope that I managed to convince you that physics and geometry are actually powerful and expressive form of inductive bias for robot learning in general. And with that, here are the references of the papers that I presented, and I'm very happy to answer questions.
Go ahead, you can ask a question.
She can hear.
Yeah, she can hear everything.
Okay. Hi, Noémie. Thank you so much for the talk. So I have a question. So I think just regarding like motion generation and motion transfer, I think the challenge like for the past decades, like it's so hard to like model every system. I think that's why a lot of focus has been shifted towards like modeling the dynamic of trajectory instead. So, but for your work, like once we have this network, I think we can always like have the dynamic of the system. Do you think we can just discard like all the previous work on like modeling trajectory instead we just now focus on like the modeling the system dynamics? I'm not sure if I make it clear because I know a lot of your works previously is like directly dealing with trajectory in the task space, and you try to like directly transfer that
Yes.
trajectory from across different embodiments.
Hmm.
So I think
Yeah,
that kind of just makes this system dynamics unnecessary since you are just focused on like trajectory dynamics. But now that you have this network to basically just get any dynamic of the system, do you still see the value of modeling the trajectory dynamics?
Yeah. I think the two things are actually complementary, if I understood the question properly. So I think you actually sometimes model the dynamics of trajectories, maybe at the task space level, because you want to, you're interested in what happened in the task space. The goal with this work was actually to go in the lower level because we wanted to be able to generate motions that were energy efficient. So the idea is that you could combine basically the dynamics that you have in the task space with the dynamics that you want to have in the joint space. So that the dynamics that you have in the joint space are energy efficient or comply the requirements that you have. So I think those approaches are complementary. It's true that what you do in joint space kind of defines what you do in task space, but you have more options. So you have several options in joint space to achieve the same task in task space. And basically this is kind of a way of designing the motion in joint space so that it's as efficient as possible. I'm not sure if I answer your question or.
Hi, Noémie. Thank you for the great talk. I have a question regarding the reduced order Lagrangian framework that you presented. You talked a little bit about this phi, which is the embedding which preserves the properties that you have in the full order Lagrangian dynamics, such as stability and safety, maybe not safety, you said stability and feasibility for in your reduced order model as well. Can you talk a little bit about what ensures this kind of preservation of these properties?
Yeah, so what ensures this is actually the fact that your mapping is an embedding. So the definition of an embedding is that every point in the reduced space maps to a single point in the high dimensional space. So basically you can see it as a kind of, you have a one-to-one mapping in a sense, because you're changing dimension, but it's a kind of one-to-one mapping from the reduced space to the full order model. And this allows you to have the conservation of these properties.
And
you can see that.
Sorry.
Yes, sorry. Go ahead.
Is it obvious to know for example, for these complex robots, is it obvious to know what these reduced order models are a priori? Do these mappings already exist for complex dynamics models? Or is there a way to is there a framework to actually does this approach actually generate these mappings as well? I don't know if that question.
Yeah. So those embeddings, basically what at the end of the day they do is that they extract the important features of your dynamics or of your motions in a sense. So you can think a little bit about it as if, when you have a high dimensional data and you reduce their dimension via typically an autoencoder. The autoencoder has a little bit the same effect in this, in that it extracts the important parts of the data and it removes or it removes the redundancy in your data. So this model order reduction, so this embedding basically does the same. So if you have really a strong knowledge on your system, you may just define the embedding by hand. In practice, usually you don't have that, and you learn this embedding. It can be a linear mapping that you learn. It can be the decoder of an autoencoder, but it's typically something you're going to actually learn.
Thank you.
Another question. So when you talk about like segmenting, you're actually in the configuration space, you mentioned you kind of just, you just try to like figure out where the cutoff is just by finding like where like the geodesics start like differing. I feel like if you just like segment that way, doesn't make like the trajectory like super sensitive to the noise. What if you configuration space like you know, like fluctuated but still follow like a general trend, but like when you like measure like the local difference, it still like changes a lot. I'm not sure if I hear the question.
So I think I lost the sound for a little bit. If you could repeat just the beginning of your question.
Yeah,
I'm
just
sorry.
like try to segment like the trajectory in the configuration space. We mentioned you just like kind of take the like the moving average, like wherever like the geodesics start like differing significantly, you kind of just like say, okay, this is a cutoff point for like the current.
Yes.
So I'm just wondering, is this method like really sensitive to like the noises? Like when you collect the trajectory, what if there's like fluctuation locally? Does it gonna mess,
Yeah.
is it gonna mess up like the segmentation?
Yes. So I think you have a good intuition there in the sense that, yes, it's indeed sensitive. If you start putting noise in your trajectory and your trajectory is jittering, indeed, your angle is big at every single time step. So what we have done in practice when we were analyzing those human motion is that we first filter the motion to remove a little bit the noise. I mean, this is what you do anyway when you have motion capture motions, you apply a filter, right? So we did that. And then what was very interesting at that point is that we actually observed that we obtained by default long geodesic segments in the kind of long parts of the motion. So if you think that you have a waving motion, you wave from the left to the right. This is one geodesic. And then at the point where you're actually changing direction, you wave now from the right to the left. At that changing point, we had a lot of those tiny geodesics, which are exactly what you're mentioning. So the trajectory here was a little bit noisy, and we had plenty of small segments. So here it kind of reflects the fact that, yeah, you're really changing direction. It's more noisy or more changing than before. So what you can eventually do is that you have a kind of heuristic that tells you that if the segments are too small, you just actually group them. And then you solve the issue somehow, the noise.
Thank you for your talk first. I might have three questions. First, when you're talking about learning dynamics, you gave an example of a non-rigid object dynamics to learn. But usually if you look at the objects, you don't have a full state information. So how do you imagine how we're going to map the observation to that state information while learning that?
Yeah, that's a good question. So it's true. For now, what we had is a simulator, and basically we have full state information. What you would do in practice is that you would, I think, couple that with a vision system. And the vision system may give you partial state information. So either you work with partial state information, or you kind of try to get a more complete state before inputting that into the system. So at that point, you kind of have to solve it, or to get the best to get the best out of your perception system as you can. So I think this is then basically rather a perception problem.
And the second question is, I mean, you told us that the last part of the frame of that very high dimensional clause simulation has some literary effect. What is the reason, that happened? What do you think?
For this cloth, So let me go back to that one.
Yeah, the video, the 600 DOF one.
Yeah.
And
Yeah, the one on the bottom right, that at the end it jitters a little bit, right?
what is the main reason of this here?
So the main reason of the jitter is that here we are predicting extremely long horizon. So we are basically predicting 2,500 steps. Existing approach usually go for 25, 100. So here we go for really a lot. And what happens is that at the end of here, the fall of the object, there is this interaction force with the sphere. And this makes at that point, the dynamics are more complex than what we have at the beginning. So it's so simply harder to predict. So we simply kind of at that point reach a little bit the limit where the predictions are very, very good, simply because we have long horizon.
And is that something that can be solved by having little more data for long horizon?
So it's something I'm not sure exactly to which extent. I think it can be probably improved. I'm not sure if with probably more data. No, maybe more data, not even. You could try to incorporate even more information about the fact that the dynamics are long-term into the model. Here, typically, we do that with the loss. So the loss is trained each time for a certain number of time steps. So we could try to have it for longer. Then it's more computationally expensive, but that could be something. So basically to add this dynamic consistency directly in your loss. Yeah, so that's where I see you could go. Maybe something here to note is that in general, if you want to control an object or manipulate an object and you want to have an estimate of the dynamics, you will have from time to time anyway, hopefully a perception input that tells you, hey, here is my new state. So I think you need long horizon, but you don't necessarily need like crazily long horizon. And I think with what we have here, it should be already sufficient if you have a decent perception system, which from time to time simply gives you again the information of where you are.
Or is there, like, or in this case, is there like a way to use the symmetry of the float elements? For example, like each element, because this is made out of same material, they will have some symmetricity in each element, like a finite element analysis or something like that. Is that also possible?
Yes, you could definitely add some kind of notion of symmetry. If you have any knowledge on the symmetry of your system, you could plug that in. You could do that with, I don't know, an equivalent network or something like that, a network that accounts for symmetries, basically.
And about the motion generation part, you showed us how the geodesic, just going through the geodesic path will just eventually end up with collision-free motion. But is that like reactive approach? Is that like if you just take a one step instead of doing any kind of optimization, will it eventually lead to the goal, right?
Sorry, can you repeat the last part?
If you just take a like reactive approach and take a one step at a time, it will eventually lead to the goal target area, target region.
Okay. So if you could basically have a kind of reactive motion generation based on those geodesics, right?
Yeah.
Yeah. Yeah, you could think about that, that's for sure. At the end of the day, what you would do, typically when you have those obstacles, you would update the manifold somehow at each time step and then refine your geodesic. So this would be possible. The bottleneck here a little bit, I think it's solvable. It's just, I think currently the bottleneck is that computing those geodesics still takes a little bit of time. So you probably cannot recompute it every single time step in real time for now.
How long does it take right now?